Welcome to the National Program on Technical Enhanced Learning lecture series. Myself Dr. Binoy Krishna Patra from the Physics Department, IIT Roorkee. Today I will be giving a lecture on the topic kinetic theory of gases. So, let me start kinetic theory of gases. Basically, the broad topic on which I will be giving this lecture series is thermal physics. In thermal physics, there are certain topics on which I will be giving. First, today I will be giving lecture on the kinetic theory of gases. First of all, what are the gases? Gases are one of the most pervasive aspects of our environment on the earth. We continually exist with constant exposure to gases of all forms. The steam formed in the air during a hot shower is a gas. The helium used to fill a birthday balloon is a gas. The oxygen in the air is an essential gas for life. There are important characteristics of the gases compared to solid or liquid. First of all, I want to enumerate them. First, gases are highly compressible in nature. Any external force compresses the gas sample and decreases its volume. If you remove the external force, gas volume will increase. So, this is the most salient character of the gases compared to solid and liquid. Gases are thermally expandable. When a gas sample is heated, its volume increases, and when it is cooled, its volume decreases. Regarding the viscosity character, gases have high viscosity. Gases flow much faster than liquids or solids. Most gases have low densities. Gas densities are of the order of grams per liter, whereas liquids and solids are grams per cubic centimeter, almost 1000 times greater. Gases are infinitely miscible, that means gases mix in any proportion, such as in air a mixture of many gases, nitrogen, oxygen, carbon dioxide, carbon monoxide, nitrogen oxide, nitrogen dioxide, etc. Now, let me come what is the idea, what is the motivation of kinetic theory of gases. To fully understand the world around us requires that we have a good understanding of the behavior of gases. The description of gases and their behavior can be approached from several perspectives. First, the gas laws are mathematical interpretation of the behavior of gases. However, before understanding the mathematics of gases, a chemist must have an understanding of the conceptual description of the gases, that is the purpose of the kinetic molecular theory. Now, what are the kinetic molecular theory in general? The kinetic molecular theory is a single set of descriptive characteristics of a substance known as ideal gas. We will explain what does it mean by ideal gas later, but all real gases require their own unique set of descriptive characteristics. Considering the large number of known gases in the world, the task of trying to describe each one of them individually would be an awesome task. Then how to solve this problem? How to simplify this problem? In order to simplify this task, the scientific community has decided to create an imaginary gas that approximates the behavior of all real gases. And in principle, in the high temperature limit and low density limit, real gas resemble like a ideal gas, but as such ideal gas does not exist in nature. In other words, the ideal gas is a substance that does not exist. The kinetic molecular theory describes that gas means that ideal gas, while the use of ideal gas in describing all real gases means that the description of all real gases will be wrong. The reality is that the descriptions of all real gases will be close enough to correct that any errors can be overlooked. That means, the algorithm of kinetic molecular theory is that initially you start with the concept of an ideal gas, then under some certain circumstances, then you calculate the quantity and let check it how much errors you have come across, and then you try to build up your equations so that it can incorporate the real nature of the gases, and again you calculate some quantity, let us tally with this experiment and it agrees well, then you say that you are approaching towards the real description of the gases, which is nothing but the real gases. Why do we need kinetic theory? Because we have laws of thermodynamics in our hand since 500 years back, and we know it explains beautifully different phenomena occurring in the nature, but suddenly why we abandoned that concept laws of thermodynamics. I will tell one by one why do we need to abandon the laws of thermodynamics and look for the kinetic theory. Classical thermodynamics is entirely macroscopic systems, Systems are described with the aid of their gross or large scale properties. The first law of thermodynamics is a relation among the fundamental physical quantities of work, internal energy and heat. That means, when the first law is applied to a class of system, a general relation is obtained which holds for any member of the class, but which contains no quantities or properties of a particular system that would distinguish it from one another. That means, the first law of thermodynamics tells that if you will give some amount, if you supply some amount of heat, let us say dq, it will be used in two ways. It will change the internal energy of the system by an amount du, and rest of the amount will be used to do the external work. That means, in mathematical form dq equal to du plus dw. But this is true for any gases. There is no quantities which can distinguish the first law of thermodynamics from one gas to other. For example, let us calculate the heat capacity at constant volume Cv, which is Cv equal to del u by del T at constant V, where u is the internal energy. This expression is true for all hydrostatic systems, whether solid, liquid or gas. But we know solid, liquid, gas, they are very much different from one another, but in this formalism of thermodynamics, there is no way to distinguish Cv from liquid, gas and solid. It enables one to calculate the heat capacity of a hydrostatic system, provided that one knows the internal energy as a function of temperature and volume. However, the other thing, once you know Cv, then you can calculate the heat capacity during an isochoric process defined by Qv equal to Ti to Tf, where Ti is the initial temperature, Tf is the final temperature, integrated Cv dt. It can be calculated once the heat capacity of the particular system under consideration is known as a function of temperature T. But there is nothing in classical thermodynamics that provides detailed information concerning the internal energy or the heat capacity. So, that forces to consider some theory, some microscopic theory which will deal the system in terms of its fundamental constituents, let us say atoms or molecules. That means, we must resort to look for some microscopic theory instead of the macroscopic theory, which is the thermodynamics. Another example of the limitation of classical thermodynamics is its ability to provide the equation of state any desired system. I will tell you what does it mean by equation of state. To make use of any thermodynamic equation involving P, V, T or their derivatives del P by del V at constant T or del V by del T at constant P or del T by del P at constant V, etcetera, one must have some equation of state. But unfortunately, classical thermodynamics does not provide any equation of state. That means, it does not provide any relation, any thermodynamic relation between the thermodynamical quantities, let us say pressure, volume or temperature. It does not have any predictive power to provide any relation among the thermodynamical quantities. An equation of state is a thermodynamic equation describing the state of matter under a given set of physical conditions. Let us say, what is the equation of state of water, what is the equation of state of steam, what is the equation of state of ice, or other way around. Suppose I have a water, suppose if I will increase its pressure keeping volume and temperature constant. So, what will happen? So, the answer of this situation will be given by the equation of state. It is a constitutive equation which provides a mathematical relationship between two or more state functions associated with the matter, such as its temperature, pressure, volume or internal energy or other some quantities, Gibbs potential, enthalpy, etcetera, depending on the physical condition. Experimental values are very often useful, but there are occasions where it is not feasible to perform the necessary experiment. Suppose, if an experiment is performed on, let us say oxygen, the numerical constants in the equation of state of oxygen only are obtained and no clue is at hand concerning the values of constant for any other gas. Now, let us say explain this thing. Suppose you want to perform some suppose you want to calculate some constant of the gas at very low temperature. Suppose let us say you want to perform experiment for liquid nitrogen, liquid hydrogen, which is not possible in the usual circumstances. So, then how to get it? So, that is the reason to obtain the detailed information concerning the thermodynamic coordinates and thermal properties of the system without having to resort to experimental measurements, we need some microscopic theory to obtain the physical properties of the system under any condition. So, we require calculations based on the properties and behavior of the particles of the system. There are two such microscopic theories existed in the literature. One is called the kinetic theory and the other is called the statistical mechanics. Both theories deal with particles, their internal and external motion, their collisions with one another and with any existing wall and their force of interaction. These two theories are microscopic theory, they deals with the constituent of the system microscopically, whereas in classical thermodynamics system have been dealt in terms of their macroscopic properties, pressure, volume, temperature, but in the microscopic theory we will deal in terms of the interaction among the constituent, how they interact with each other, etc. Making use of the laws of mechanics and statistics, kinetic theory concerned itself with the average motion of atoms and their collisions with the walls and other objects in order to calculate the equation of state for the ideal gas. whereas statistical mechanics avoids the mechanical aspects of the particles and deals with the energy aspects of aggregates or ensembles of the particles. Actually, statistical mechanics is based on the concept of ensemble theory, but right now I will not talk about the ensemble theory. It is an assemble of particles which can mimic a given system. There are three kinds of ensemble. One is known as microcanonical ensemble, canonical ensemble and grand canonical ensemble. However, these things will be dealt in the statistical mechanics, but for the sake of this present lecture series, I will confine myself only in the kinetic theory of gases. Statistical mechanics relies heavily on statistics and quantum mechanics. Only equilibrium states can be handled, but in a uniform straightforward manner, so that once the energy levels of the atoms or systems of atoms are understood, a program of calculations yield the equation of state, the energy and other thermodynamic functions as well, which is known as the partition function formalism. Actually, in statistical mechanics, first of all you have to know what is the energy spectrum of the system. Basically, you have to solve the Schrodinger's equation to get the eigen energy spectrum. Once you got the energy spectrum, you calculate the partition function, and once you got the partition function, you can calculate all the quantities as you want. Suppose you want to calculate, you can calculate the pressure, you can calculate the entropy, you can calculate other thermodynamical quantity, let us say internal energy, Gibbs potential, enthalpy or any other quantities if you want, you can get it. However, we shall limit ourselves to a small part of the kinetic theory of the ideal gas. The kinetic theory of gases was the result of the early 19th century work of Avogadro and Loschmidt, who calculated the number of atoms or molecules in a molar volume of a gas. In an unpublished work, Waterstone recognized that temperature is a function of the motion of the particles of a gas, but Chronic is commonly recognized as the originator of the kinetic theory of gases in 1856. Now, let me start what are the basic assumptions is made for the kinetic theory of gases. However, here we will deal the kinetic theory of the ideal gases. Not only that, we will deal a gases or monoatomic gases. So, first of all we will discuss in details what are the basic assumptions are made for the kinetic theory of gases, and then how using those basic assumptions how to calculate the pressures and other quantities. Let me start it. In order to formulate a microscopic theory of gases which will be limited to monatomic gases, several simplifying assumptions about the behavior of atoms of the ideal gases are made. First, any small sample of gas consists of an enormous number of particles. For any one chemical species, all atoms are identical and inert. If m is the mass of each atom, then the total mass is m into n, and if m denotes the molecular mass in kilograms per mole, formerly called the atomic or molecular weight, then the number of moles n is given by small m into capital M by capital M. The number of particles per mole of gas is called the Avogadro number Na, which is defined as the total number of particles n divided by number of moles, or in terms of molecular weight divided by A, which is nothing but 6.022 into 10 to the power 23 number of particles per mole. Since a mole of ideal gas at the freezing point of water and at standard atmospheric pressure occupies a volume 22.4 liter. So, there are approximately 3 into 10 to the power 19 atoms in a volume of only 1 centimeter cube, whereas 3 into 10 to the power 16 atoms per cubic millimeter, and even a volume as small as cubic micrometer contains as many as 3 into 10 to the power 7 atoms. So, that means the assumptions that any small sample of gas consists of an enormous number of particles, it is justified for the ideal gases. Next, the atoms of an ideal gas are supposed to resemble small hard sphere that are in perpetual random motion. Within the temperature and pressure range of an ideal gas, the average distance between neighboring atoms is large compared with the size of an atom. So, this assumption justifies that ideal gas means there is no interaction among the constituent of the gases. So, this is justifies since the average distance between the neighboring atoms is quite large compared to the size of the atom. Let us take some let us do some calculation. The diameter of an atom is of the order of 2 to 3 Armstrong. Under standard conditions, the average distance between atom is about 50 times their diameter. That means, the interactions among the constituents are very small. So, they can be treated as a free streaming particle inside the container of the gas. Third assumption is the atoms of an ideal gas are assumed to exert no forces of attraction or repulsion on other atoms except when they collide with one another and with the wall. Between collisions, they move with uniform rectilinear motion. Fourth assumption is the portion of a wall with which an atom collides is considered to be smooth and the collision is assumed to be perfectly elastic. Okay. So, this is the one of the most important assumptions in the kinetic theory of gases, that the collisions between the atoms and the walls of the container is perfectly elastic collision. To make the elastic collision, so that is the reason the surface of the wall should be smooth enough, so that collision will be perfectly elastic. So, as we know, if v is the speed of an atom approaching a wall, only the perpendicular component of velocity v perpendicular is changed upon collisions with the wall. From v perpendicular to minus v perpendicular, just it changes its sign, or a total change of minus 2 v perpendicular. Fifth assumption, when there is no external field of force, the atoms are distributed uniformly throughout a container. The number density n by v is assumed constant, so that in any small element of volume dV, there are dn number of atoms, where dn is n by v into dV. Now, let me start what is the concept of an infinitesimal volume element in the kinetic theory of gases. As we know, in the thermodynamics, the infinitesimal volume element is defined as the volume element which are too small compared, which are very much small compared to the volume of the system. So, same concept of an infinitesimal volume element also holds good in the kinetic theory of gases. Let me justify that statement. The infinitesimal volume element dV must satisfy the same conditions in the kinetic theory as in thermodynamics, namely it is small compared with V, but large enough to make dn a large number. For example, a volume of 1 centimeter cube contains 10 to the power 19 atoms, which is quite large. Then 1/1000th of a cubic centimeter would still contain very large atoms, 10 to the power 13 atoms, and would qualify as a differential volume element. So, what is the idea of differential volume element in kinetic theory of gases? These volume elements should be very small compared to the total volume of the system, but simultaneously it should contain a very large number of atoms, so that it should satisfy the first assumptions in the kinetic theory. Let me show you that any small sample of gas consists of an enormous number of particles. So, it should satisfy the first assumptions of the kinetic theory. Assumption 6, there is no preferred direction, there is no preferred directions of the atoms which are moving in a random motion. That means, I can find the equal number of atoms in any directions. Okay. So, there should not be any preferred direction for the velocity of any atom. So, that at any moment there are as many atoms moving in one direction as in another. This is the most crucial assumptions in the kinetic theory of gases. Seventh, so not all atoms have the same speed. A few atoms at any moment move slowly and a few move very rapidly. So, that speeds may be considered to cover the range from 0 to the speed of light. However, no atoms can achieve the speed of light, but for the sake of calculations we can take the velocity from 0 to infinity. However, there will be no error introduced, because there are no atoms which are velocity whose velocity ranges from the velocity of light. So, since most atomic speeds are so far below the speed of light, no error is introduced in integrating the speed from 0 to infinity. Now, let me summarize the assumptions which we have made and which we have discussed already in a very short form, okay, and which will be used in doing the calculation. First assumptions we have made: gas consists of large number of particles, either it may be atoms or molecules. Particles make elastic collisions with each other and with walls of container. There exist no external forces, that means where density, in that case density will be constant. Particles on average separated by distances large compared to their diameters. No forces between particles except when they collide. These are the main assumptions we have made. Now, on the basis of that assumptions, we will try to calculate the pressure from the kinetic theory of gases. Suppose if dn number of atoms having speed between v and v plus dv, it is assumed that dn remains constant at equilibrium, even though the atoms are perpetually colliding and changing with their speed, but dn remains constant at equilibrium. Since the velocity vectors of the atoms of the gas have no preferred directions, as I have already mentioned in one of the assumptions, that there are no directions are preferred. So, consider an arbitrary velocity vector v directed from the origin as in figure to the elementary area ds prime. Let us show this figure. So, this is the elementary area, this is the elementary area ds, as you can see in the figure. So, some velocity vector which is directed from the origin along the radial directions. So, the elementary area is normal to the r vector. So, in that case let us know how many atoms have velocity vectors in the neighborhood of v. The calculation of this quantity involves the concept of a solid angle. So, let me first calculate what is the solid angle. Okay. Taking O as the origin of the polar coordinate r theta phi, we construct a sphere of radius r. The area ds prime on the surface of the sphere formed by two circles of latitude differing by d theta and two circles of longitude differing by d phi has the magnitude ds prime is r d theta into r sin theta d phi. Okay. So, this is the figure, this is the ds infinitesimal area, you can see in the figure. So, then the solid angle d omega formed by lines radiating from the origin and touching the edges of ds prime is by definition is d omega is ds prime by r square, which is r d theta into r sin theta d phi by r square, which is nothing but the sin theta d theta d phi. This is the solid angle. Now, since the largest area on the surface of the sphere is that of the entire sphere 4 pi r square, the maximum solid angle is 4 pi. So, now we want to calculate what are the fraction of atoms with velocity vectors in the neighborhood of velocity v. We will have speeds between v and v plus dv and directions within the solid angle d omega around v. If dn is the number of atoms with speed between v and v plus dv, then the fraction of these atoms whose direction lies within the solid angle d omega is d omega by 4 pi. So, the number of atoms within the speed range dv means within the speed range between v and v plus dv, angle theta and theta plus d theta and phi and phi plus d phi is given by dq n v theta phi is dn into d omega by 4 pi. This equation express that atomic velocities has no preferred direction. So, that is the reason you got the term d omega by 4 pi, which emphasizes the fact that atomic velocities has no preferred direction. That means, atoms will move randomly in all possible directions. Second, now consider this group of atoms approaching a small area ds of the wall of the containing vessel. Many of these atoms will undergo collision along the way, but if we consider only those members of the group that lie within the cylinder whose side is of length v dt, where dt is very small time interval where no collisions are made. In that case, all dq n v theta phi atoms within this cylinder will collide the atoms containing in the infinite small surface area ds, okay, as you can see from this figure. Okay. All the atoms in the cylinder of length v dt strike the area dA at the angle theta to the normal. The perpendicular component of velocity is v cos theta, which will be reversed because of elastic collision, but the parallel component which is v sin theta, which remains the same. Now, the volume of the cylinder is dV is v dt cos theta into ds, and if v is the total volume of the container, only the fraction dV by v of the atoms will be contained within the cylinder. So, now finally, we want to calculate what are the total number of atoms in the velocity range with the speed v and v plus dv, in the theta range theta and theta plus d theta, in the phi range phi and phi plus d phi. Okay. So, therefore, the number of atoms in the speed range v and v plus dv, in the theta range theta and theta plus d phi, in the phi range phi and phi plus d phi, striking ds in time dt is dq n v theta phi dv by v. So, this equation emphasizes this fact that atoms has no preferred locations. So, atom can stay anywhere in the container. So, that makes the quantity dV by V. Okay. According to our fundamental assumptions, an atomic collision is perfectly elastic. It follows therefore, that an atom moving with speed v in a direction making an angle theta with the normal to a wall will undergo a change only in its perpendicular component of velocity. There will be no change in the horizontal component of velocity, which will remains unaltered. So, finally, we want to calculate what is the total change of momenta in the per collisions. Okay. So, it consists of three terms which we have already derived. One is based on the concept of there is no preferred direction, second one is based there is no preferred location of the atoms. So, using these two assumptions, let me calculate what are the total change of momentum per collision. Okay. As we know, change of momentum per collision is minus 2 mv cos theta, where basically v cos theta is nothing but the perpendicular component of velocity. Let me show you in the figure. Yes, in this figure you can see that v cos theta is the perpendicular component of velocity, which can only be changed by the amount minus 2 v perpendicular, that is given 2 m v cos theta. Okay. So, total change of momenta consists of 3 terms. First term is number of atoms of speed v in the solid angle d omega, which is d n into d omega by 4 pi, fraction of these atoms striking d s in time d t, which is d v upon v, and change in momenta per collision, which is minus 2 m v cos theta. So, we have got 3 terms, and if we will product them together, we got it d n by 4 pi sin theta d theta, which is nothing but the d omega, and d v, as we have already done, d v is v d t cos theta d s. So, 1 by v d t cos theta into d s into minus 2 m v cos theta. So, finally, we got the total change of momentum per collisions. Okay. The change in momentum per unit time and per unit area due to collisions from all directions is the pressure d p exerted by the wall on the d n gas atoms. So, using the symmetry argument, we know since they are coming from all possible directions. So, we can reverse the sign minus 2 m v cos theta is by 2 m v cos theta is d p equal to m v square d n by v 1 by 2 pi 0 to 2 pi d phi 0 to pi by 2 cos square theta sin theta d theta. 2 m v cos theta, 2 in m v cos theta we will cancel with the 4 pi, makes it 2 pi. Now, if I will do this angular integration, I will get it, I will get a factor 1/3, which what does it physically mean? Physically it means that particles are coming from all possible directions. So, this is, and all possible directions are equally probable. So, that means you will get 1/3 term by automatically. That means, this is the concept of isotropicity in the momentum space. When the average values of V x square will be same as average values of V y square as average values of V z square, then average values of V square is nothing but 1/3 average values of either V x square or V y square or V z square. That is the physical meaning of 1/3. So, after doing the angular integration, the total pressure due to atoms of all speed is given by P v equal to 1/3 m 0 to infinity v square into d n. As I have already told you that I will integrate velocity from 0 to infinity, although no atoms have speed greater than the velocity of light, but still I can write it 0 to infinity, because I will not do any mistake in doing the integration, because there are no atoms which have velocity of greater than the velocity of light.